Hi, I'm going to present the study we made with the title of Investigating the Influence of Mechanical Property Variability on Dispersion Diagrams using Bayesian Inference. The authors of this study are me, Luis, Vinícius Dopogeto, and José Roberto Arruda from the State University of Campinas, Danilo Belli from the University of São Paulo, and Adriano Fabro from the University of Brasilia. As you can see, I'm going to present a brief introduction on the problem and the objectives of our work. Then, in the methodology topic, I'm going to present the deterministic model and the Prony's method that we used in the MCMC algorithm. And we are going to present the statistical analysis. In the results topic, I'm going to present the estimated distributions, the deterministic response as an example using the mean values, and the stochastic response. And finally, we are going to present the conclusions and acknowledgements. The variability of mechanical properties can influence significantly the wave propagation analysis of structures, and the spatial cases where the structure is a periodic structure. However, only in recent studies, works where those characteristics were considered were reported in the literature. In this way, a probability density function can be used to quantify uncertainties related to those parameters, but this usually requires a large sample size. In this way, we can use a Bayesian statistics method that usually yields less biased estimates and improves precision and accuracy by introducing a prior information that usually comes in the form of a prior distribution. The objective of this study is to develop a more precise estimation for the mechanical properties. We do so by introducing in the MCMC algorithm that we use to estimate the posterior distribution for the Bayesian statistics via using the estimated value for the wave numbers that we obtain from the FRFs and using the Prony's method and comparing to the model values for the wave numbers. By doing so, we can obtain a more precise estimation for the mechanical property, and by the end, we can also apply those distributions and a traditional Monte Carlo method to estimate the stochastic response for the wave number. And using the stochastic wave number, we analyzed the robustness of the bandgaps. Here we have the element we are going to apply this methodology, which is a plane frame, which has the behavior of a beam and a rod uncoupled, where Ui is the flexural displacement, Ux is the longitudinal displacement, and Q is the applied force or bending moment. And we also have the governing equation of motion for the rod and beam, where E is the stiffness, A is the cross-sectional area, ρ is the mass density, and I is the second moment of area. In addition, with the analytical solution, we can obtain the spectral element method that relates force and displacement via the dynamic stiffness matrix on the frequency and wave number domains. With these relationships, we can obtain the FRF, the frequency response function, for a segment by using this matrix form. Then, for the Prony's method, we use the analytical solution, which is the sum of two imaginary exponentials if the wave is far from the ends of the structure. As we are analyzing a geometrically periodic structure, we have to take the FRFs with a equally spaced distance equal to the cell length. That's because as the wave number changes throughout the structure and we want to estimate the equivalent wave number, this condition has to be fulfilled. Then, after some manipulations and multiplying each line by a different constant, we can obtain for 3 observations the equation 7. Then, after manipulating equation 7 and adding all these equations, we can obtain equation 8. And one possible solution for this equation is where both sides are equal to 0. And this is the equation that we use. Considering the parameter eta2 equal 1, we obtain the same equation in a matrix form as represented as equation 11. And when we have more than 3 observations, we can use the least square Prony method to estimate the parameters eta0 and eta1 as equation 12 shows. The vector of parameters eta can be obtained via a generalized inverse, and after this vector is obtained, we can use them on equation 9 to obtain the exponentials, which has the wave number inside. The Bayesian statistic is based on the Bayes theorem. Therefore, the posterior distribution can be obtained by the product of the likelihood function with the prior distribution and divided by a normalizing constant. For the prior distributions, for each mechanical property, the stiffness and mass density, we obtained from 2 reported studies values for the same material. In the present work it was nylon, and for each parameter we fit the gamma distribution with the minimum value observed in the literature as the 2.5% quantile and the maximum value as the 97.5% quantile. For the present study, we consider that the mechanical properties E and ρ follows a gamma distribution, which has a scale and shape parameters, and assuming that we have n observations and all these observations come from the same random variables, they are independent and identically distributed, IID. Then, the likelihood function is given by equation 18, which is the product of those PDFs. In order to simplify the calculations, we can apply the logarithm of the likelihood function, which is called log likelihood, and in this case is given by equation 19. Using all the values we obtain in the literature and considering that E and ρ follow a gamma distribution each, we use the maximum likelihood method to estimate their distributions. Then, with these distributions, we could simulate n values for E and ρ, and we also simulated FRFs equally spaced throughout the finite structure. Then, using these FRFs, we could estimate the wave number values, which here we considered as a observed wave number values. In addition, we are going to present some sample statistics, which are the mean and variance, presented as equation 20, and we also have some important relationships as equation 21. Here we have a graphical representation of the used MCMC algorithm. We first define the prior distribution and the likelihood function, and we also give the model for generating the FRFs and for estimating the wave number values. Then, defining a initial value in the parameter space, we use the Monte Carlo combined with Markov chain method to random walk and accept or reject the tested value based on the values of the prior distribution evaluated for those 2 values for the parameter, and we also evaluate for the likelihood function, and we also use the difference between the observed wave number, the considered value as the observation for the wave number, and the value we obtain in the model. Then, after a defined number of steps, we have the final result, which is a distribution called the posterior distribution. Now, going throughout the MCMC algorithm with more details, we first define the size of the chain that represents the parameter distributions, and we also define the initial values for the parameters. Then we sample new values for the parameters in the parameter space that we considered here as a uniform distribution, and we evaluate the likelihood function, the prior distribution, and we also calculate the difference between the values obtained from the model and the observed wavenumber values. Then we obtain the matrix called Ry for 0, which is the initial value, and 1 for the new value that we sampled from the parameter space. We then calculate the matrix R10, which is the ratio between R1 and R0, and we sample a value from the uniform distribution from 0 to 1. This number is called U. If R10 is greater than 1, or if U is smaller than R10, then we accept theta 1 as theta 0, and theta 1 also becomes a chain value. Otherwise, theta 1 is rejected, and we sample again considering the same theta 0. After we obtain a chain that represents the posterior distribution, we have to assure that it converged. We used 3 methods to assure its convergence. It was the Guick's criterion, Heidelberg-Welch test, and the Hafter-Lewis method. In the Bayesian statistics, the posterior distribution has all the information the researcher has related to the problem, and any statistic, such as mode, median, or mean, can be used as a estimator. And for the present research, we use the mean for the estimation. In addition, we can use any kind of interval to give additional information related to the parameter estimation. For the present research, we use the highest posterior density, which is the interval in the parameter space that has the shortest distance between the inferior limit and superior limit. The base factor gives a ratio of chance of the realization of theta being in the theta 1 over theta 0, where theta 1 and theta 0 are disjoint parts of the parameter space. The base factor was used to test the robustness of the stochastic bandgap. The calculation of the base factor is given through the ratio between the posterior and prior ratio of chance of theta being equal theta 1 over theta being equal theta 0. Using the base factor values, we can transform them into qualitative evidence using the Jeffreys scale of evidence. As we can see, according to the value that the base factor has, we have the evidence against the H0, which is the evidence of theta being equal to theta 0. In other words, we have a evidence in favor of H1, which is theta being equal theta 1. Using the previously stated methodology, we can obtain the prior distributions and the likelihood functions. Then we can simulate some values that we consider as observations from the properties E and ρ. We also have some statistics that we need for calculating the log likelihood, and using those simulated values, we simulated some FRFs that we used in the Prony's method to calculate the wavenumber values that we considered as observed wavenumbers. Here we can see the results for the posterior distributions. At the first table, we have the results when we use the OpenBug software, and at the second table we have the results when we use the used MCMC algorithm. We can see that all distributions converge considering the convergence test, and we see that the mean is relatively near each other for the same parameters. However, when we compare the 8PD interval, the second method for this distribution has a more precise estimation. Here we have the graphical representation of the two estimated distributions when we use the used MCMC algorithm. Considering this geometrically periodic structure, we can see that when we use the mean values for the estimated distributions, we can see that there are two band gaps for the longitudinal wave, and there are also two band gaps when we consider the transverse wave. Now, considering the same response as the deterministic one, we now analyze only the imaginary part of the wave number. As we can see, for the deterministic response there are two band gaps, but when we use the distribution estimated via the OpenBugs software, we can see that there is a moderate evidence of a band gap, but only in the first band. Then, when we use the distribution we estimated using the proposed MCMC algorithm, we can see that there are two band gaps as a definitive evidence level. This is because there is a relationship between the uncertainty and the dispersion of the estimated distribution. Using again the estimated distributions via the proposed MCMC method, we can see that there are a decisive evidence of two band gaps similarly to the longitudinal wave numbers, but now for the transverse wave number. The conclusions of the present research are that there are two complete and robust band gaps to the mechanical properties for the proposed mechanical properties variability and for the proposed structure. And the proposed MCMC algorithm incorporates the use of the wave number values and reduces uncertainties when compared to the one using only prior and likelihood function. The authors are grateful for the financial support of the FAPESP and the CNPq. And here we have the main reference we used in the current study. Thank you all for your attention.